Okay, let's continue our discussion of lighting and shading. And what we're going to do in this lecture is move from the ideas of specular, diffuse, and ambient terms from last lecture and get into more details of the model, but also introduce a modification of the basic Phong model called the modified Phong or Phong Blin or Blin Phong model. And then we'll look briefly at the vectors that we need to compute for that model. And then in the next lecture, we'll actually start looking at code in WebGL that implements this. So let's start with the easy one, that's ambient light. And we said that's how we account for all these multiple interactions of light bouncing around the room. And it's important to remember that the ambient light is not just a constant that you specify. It's actually a constant that's a product. Well, you obviously specify it, but it's a product of a factor that has to do with the surfaces, how much they absorb, and a factor that has to do with the overall color of the room. So if you're in a room that has, say, red walls, the ambient light that it contributes to your shading and lighting is going to be colored red. It's also important that it depends on there being a light source. If you're in a room with red walls and you want to add an ambient term that's dependent on it, you need to have the light on. So it's not simply a constant. We want to keep it as a product of two other constants. One is we can call it a reflection component, Ka, which is the reflectivity of the room or environment as a whole, which will have a red, green, and blue component. It's important to interpret all of these terms that I'm going to talk about, instead of writing them as the red component, the blue component, the green component. What I'm going to do is just write them down once with the understanding that every time we do that, we really are going to do it 3 times individually for the 3 red, green, and blue components of the lighting. So there's going to be a reflection coefficient, and then there's going to be a term that's dependent on the intensity of the ambient light, which in a way is proportional to the intensity of the total light from the sources in the scene. So there's going to be that, and we'll call it the ambient product, and now we'll derive a diffuse product and a specular product. But once you fix those constants, that's a constant in the model that applies to every vertex or every fragment in the scene. Okay, now the distance term we said is going to be, we want it in there because we want to get, for point sources, to not have the harsh lighting and to have some sort of smooth transition from surfaces that would be in shadow to surfaces that would be lit. And one way to do that is to include this distance term. The other thing is, just on an energy basis, we know that the energy is going to go down as the distance squared from between the light and the light source and the surface that it hits. So we can have a 1 over d squared term, but we soften that up. That tends to be a little harsh. So we soften that up by having some sort of a quadratic term with a constant and a linear term. Actually, there's a little error here. This should just be a constant a, not a times d, but a quadratic term. And I'll leave this out in most of what we have, but with the understanding that it's easy to stick that in later. Okay, so now what about the sources? Now in the Phong model, what we said was that there was going to be a different source potentially for the ambient, diffuse, and specular components. Now this is kind of a kludge, because if you have a light, there's a light sitting there, it has some properties and it's not separate red, green, and blue. But not separate ambient, diffuse, and specular. But we're trying to build a model that's simple to compute and gives us reasonable accuracy, in the sense that it looks okay. And so the one way to do that is to handle the diffuse, specular, and ambient terms individually and separately, and therefore we need to look at the sources for those terms separately. So we're going to say, okay, that a light source has an ambient component in red, green, and blue. It has a diffuse component in red, green, and blue, and it has a specular component in red, green, and blue. So we need 9 coefficients to identify the light coming from a point source. Now, why are those colors going to be different? Well, think back to the example we talked about of having an apple with a shiny highlight. And we said that that highlight is really a reflection of light in the room. And so if we wanted to get that kind of a highlight for the specular term, we'd want to have the specular light being somewhat whitish and the surface properties being somewhat whitish for the specular term, while for the ambient term we might, for the diffuse term we might want to have a different components for the light. Actually, in practice, what you'll wind up doing a lot is having the ambient light, the diffuse light terms and the specular light terms being the same, and the ambient terms being a little different because they reflect the total environment. And it's not uncommon also to use the ambient term with just a little bit of white light to sort of make sure that all of your objects are illuminated. And often that's a starting point to see if everything is correct, to put in just that little bit of ambient light and leave the rest as zeros. Okay, now what about the material properties? For every incoming component for each of red, green, and blue, and each of specular, diffuse, and ambient, there's going to be a corresponding reflection coefficient, which tells you how much of the light of that component is absorbed by that material. So there's going to be 9 material constants. We'll call them Ks. So KDR is for the diffuse red component, KDG is for the diffuse green component, and so on for the others. One more term we have to add is that in the Phong model, there was a shyness coefficient because we raised that dot product to some power alpha, where the higher alpha was, the shinier it would look. It would narrow the angle at which light would be reflected. So we have a 10th parameter we have to specify for that. So there's a lot of components, and we'll see that when we see our examples. There's a lot of statements that say, here's the diffuse components, here's the specular components, here's the ambient components, and we'll send them over to the vertex shader or actually maybe compute the light within the application. There's a bunch of constants to specify. Okay, if we add that all together and put it together with what we talked about in the last lecture, then here's the model without the distance term. Okay, so here's the diffuse terms. Remember, the diffuse term went down as the virtual sun went down in the sky. It was proportional to the angle, the cosine of the angle between the light source and the normal at that surface. Again, this has to be interpreted. This is a term that we do for all the reds, we do it for all the greens, we do it for all the blues, and we also do it for each light source. So that the lighting computation can take quite a while if you have a lot of sources in the scene. Okay, so here's the diffuse term. Here at the end is the ambient term, which just doesn't depend on the point where the point is located. It just depends on the absorption of that material and the incoming ambient light. And here's the specular term, which again has a reflection or absorption constant, the strength of the incoming light for each component, and then the dot product, the cosine of between the vector to the viewer and the angle of a perfect reflection, and we have to compute that angle. We'll come back to that in a minute, raised to the alpha power. So here's the standard lighting model, the Phong model, and then we add if you like, we add on the distance term by dividing by that quadratic. And that's almost the standard model. The one that we actually will wind up using most of the time is one slight modification, which is called the modified Phong model, which Blin said, let's use a slightly different term for the reflected, for the specular component by using something called the halfway vector and the halfway angle. We'll see that in the next slide. One of the reasons that he proposed that is the calculation is a bit more efficient than the calculation of the Phong model, and there's also some physical justification for why this is a pretty reasonable approximation. So he said, let's use, instead of what we had for the specular term, let's define this vector h, which is halfway between the light source coming in and where the viewer is. So here's the viewer, here's L, here's the halfway vector, which defines a halfway angle, which is a little bit different than what you had here. Before we were talking about this angle phi here between the reflected vector and the angle towards the viewer and the angle of the perfect reflection. The angle we're actually going to use is the dot product between this halfway vector and the normal vector, so we get this angle psi. And in this diagram, it looks like, well, gee, psi isn't that much different from phi. In fact, they're sort of proportional. You can show if everything was coplanar, it would be twice this angle, so you can always have the contribution. But as I said, the main justification here is that this is much more efficient to compute, and so we just replace v dot r to the alpha power by n dot h to the beta power, where what we can do is try and pick a value of beta that will give us essentially the same contribution as this for a given alpha. So here's the point I was looking for. It's half of the angle you had here if the vectors are coplanar, and that's one. There's also another physical justification for how you would orient the surface to get the maximum reflection. Now this model is what's specified in the OpenGL standard. So even though the functionality in modern desktop OpenGL has been deprecated, all of these functions for defining materials and light sources in this model were part of the fixed function pipeline, and this model was actually built into hardware when they started using VLSI chips to build their first hardware pipelines. So it's there in the standard, and it's, for the kind of computation, the amount of computation, it's a pretty good model. And here's I love this next slide. This is an old slide. You can actually find the code. Just look up SGI teapots. That Silicon Graphics did this example long, long ago. And these are teapots. We'll be talking later about the teapot model when we talk about curves and surfaces. It's sort of a standard object that's used in computer graphics because it's kind of cute. It has a lot of different curvature surfaces. It's made up of a bunch of little Bezier patches, but you can approximate them with polygons. So the important thing here is that every one of these teapots is the same geometric object, but every one has different parameters used in the modified Phong model. So some of them will look like very dull surfaces like this one. Others will look more like very shiny metal with this nice specular highlight. Well, look at this one. This one, you can tell, is shinier than this one. So the color reflection components are probably pretty close in this case, but this one has a much higher shininess component, and this one has an even higher shininess component. So, and then you can see the same kind of differences between these two yellowish or goldish ones. So this shows you the kind of things you can get by just playing with parameters in that modified Phong or blend Phong model. Now, what about the vectors? Well, we've talked a little bit about that. That L and V are things, the angle to the light source and the vector to the viewer. Well, those are things that you specify in your application. You're going to say, where is the camera, where are the objects, and where are the light source. So that's simple. We talked about computing R, the angle of a perfect reflection, from these two other, the vector towards a perfect reflection. From these other two vectors, I'll come back to that in a second. The real issue is, what is the normal at the surface? And that's a tough one because OpenGL really doesn't tell you anything about what your surfaces are, and certainly not in WebGL. But even in the old fixed function pipeline, what the normals were, well, that depends on how you choose to model your surfaces. Now, we'll see a little more of that at the end of this lecture, but basically it's up to you and your application to determine the normals, and the usual thing is you determine them depending on what your kind of surfaces you're using in your model, and then you define a normal vector, and that becomes another attribute like the positions and the colors, and you either use that in the application or send it on to the shader as any other attribute. There are some exceptions that were easy, that were in the fixed function pipeline, in particular quadric surfaces like spheres and cones and cylinders. You can compute those those normals analytically, and you can do that for polynomial surfaces, where parametric polynomials, usually cubics, are used to define the surface shape, and we'll see a little more of that in a little bit. Okay, so let's look at those angles. Here's the reflection angle. Again, if you're going to use it do the shading within the vertex shader or the fragment shader, GLSL has a reflect function that you just give it ln n, and it'll come back with this with R. And again, the assumption here, I should have mentioned a couple slides ago, is all of these have been normalized. They all have unit length, so this is what we get, and we assume in that model that we had, the modified Phong model, all the vectors have been normalized. Okay, so if we used again the two facts that the angle of incidence is the angle of reflection, and all three of these vectors have to be coplanar, you get two equations and two unknowns, and you can solve for the vector R and make it have all unit length, and this is what you get. Okay, now what about the normals? Let's at least finish up today by looking at the normals for some simple surfaces that we deal with. Obviously, the most simple one is, what do you do when you have flat polygons like triangles? Because that's what we're going to render. So what we can argue is this, that if we have a plane, it's described by, this is one way of describing it, by this implicit equation, but we also know that it is specified by 3 points. If I give you 3 points that are not all on the same line, they determine a triangle, but they also determine the plane that triangle lies in. And if I know the equation of that plane, I can get the normal. And in fact, A, B, and C are that normal, because if you look at AX plus BY plus CZ, that's a dot product of ABC with XYZ. And if, well, let's argue this, that D equals 0 is parallel to every other plane for every other value of D. So if I write a vector ABC and a vector XYZ, this is the dot product of those two vectors equal to 0, and therefore these two vectors are normal to each other, or perpendicular to each other, and therefore ABC is the normal to that plane. Another way to look at this is that if I have those 3 points that determine this plane, then I could take the cross product of any two vectors that lie in the plane, and they will have to be normal to it. I have to be a little careful here of the order to make sure if this is an outward pointing face, the normal is pointing in the outward direction. But suppose this is P0, P1, and P2, then, I probably should have drawn this as a triangle, because you'll probably be dealing with triangles, but if I have those 3 points, then the vector P1 minus P0, determined by these 2 points, lies in the plane, as does the vector P2 minus P0, and their cross product, therefore, must be normal to the plane. So this would be probably the most useful method to you, that if you're working with triangles, you have the 3 vertices of the triangle. If I have the 3 vertices of the triangle, I could always find the normal at that point, and then stick it into a vec3 or a vec4, and now it's just another attribute that I send to the shaders. What about a sphere? We're going to have some examples soon of shading a sphere. It's in the reading. I'm not going to go over this one part in class, but if you do recursive subdivision starting with a tetrahedron, you can get as close an approximation to the sphere as you want, and that code's in there. It's also discussed in the book. But so shading a sphere is kind of nice, because it gives you a way of working with surfaces that have curvature, unlike the planes we've been talking about that are flat. It's also nice because the curvature is the same everywhere. So suppose I talk about what is the equation for a sphere, and let's center it at the origin. So it's something like, x squared plus y squared plus z squared equals r squared, okay, if it's centered there. Or I can also do it using vectors. If x squared plus y squared plus z squared equals, say, 1, then x squared is just x times, this is x times x plus y times y plus z times z. But if the vector p is x, y, z, it's just the dot product with itself, or the length of p squared. So here's the simple vector form equation of writing the equation of a sphere centered at the origin. Now, if I want to know the normal at any point, it actually points to what's called, it's given by the gradient, which actually points from the center to that point. So for a sphere, if you draw a line, or let's say a directed line segment from the center through that point is normal to the sphere at that point. Another way to derive exactly that from this equation is to say the gradient, the first component is the partial derivative of the function with respect to x. That's just 2x. The partial derivative of the function x squared plus y squared plus z squared with respect to y is 2y. Likewise for z, the derivative with respect to z, the partial derivative, is 2z. That's going to give me a normal p. Well, that's 2 times p, but we can normalize that to have unit length, and we say that the unit normal to the unit sphere at any point p is just the value of p itself. So that's a very easy one to work with. You can also do it directly from the parametric form. If you want to do lines of longitude and circles of longitude and latitude, these are the equations that they would satisfy. So we have a 2-parameter family of functions for x, y, and z, and then we could say, oh, what is the tangent plane? Well, any of you who took calculus, calculus 3, would have seen this in vector analysis, that this gradient with respect to u is a vector pointing in this plane, and so is the gradient with respect to v. That lies inside this plane. If they both lie inside this plane, their cross product must be normal to the plane, and we get n. But if you actually apply that to these equations, you'll get exactly what we had for the implicit form. We better get the same thing, which is just that the value of the normal for a sphere at any point is equal to the point you're at, normalized. Okay, so we can do the two ones that are probably the most important to us for doing demonstrations. If you use the same kind of argument on quadrics, it's easy to write down equations for cones and cylinders and other kinds of quadrics. You can get the normals pretty easily. Later we'll show, when we talk about Bezier patches in chapter 11, you'll see it's very easy to get the normals for any kind of patch. But mostly for now, I'm just going to ask you to be able to work with spheres, with planes, and perhaps with other kinds of quadric surfaces. So next couple of lectures, we'll start looking at the code to generate shaded images, and we'll also have to consider, where do we actually carry out the computation? Do we do it in the application to compute a color for each vertex? Do we do it in the vertex shader, or we do it in the fragment shader? And we'll be looking at all three cases.